So without too much Calculus 3 theory, we can just briefly talk about partial derivatives. And the idea behind partial derivatives is that if you have a function that has two variables, x and y, then you can take the derivative of that expression with respect to x with respect to WRT. So to distinguish a regular derivative with only one variable with a partial derivative with more than one variable, they use this strange looking D. It's not exactly a D, and it's not a Greek letter D, because the Greek letter D is delta. So this is a special symbol that they use called the partial symbol to denote that you're taking the derivative of something that has more than one independent variable. Now the straight D's deal with the regular derivative, and when we start talking about what's called a differential, we're going to use those straight D's as a differential, part of the differential. So you would guess that the partial of f with respect to y is going to be the derivative with respect to y. And all you're doing when you're doing that is that you're pretending that the other variable is constant. And then you take the derivative with respect to the variable that you're focused on. Sometimes they denote the partial of f with respect to x, just to make it a little bit simpler, as they use a subscript notation. And I think we saw that on the first day when we were talking about classifying the differential equations and taking a look at the difference between an ordinary differential equation, which is what we're dealing with, versus a partial differential equation, which deals with partial derivatives. So what we're going to be dealing with are differentials that have the dx and a dy in it. And of course, we're not doing the third semester calculus. We're not going to be dealing with the dz business. And so there's a special case where the function is equal to a constant, and so all you really have is x and y. And for that, we can come up with a simple example. We have this circle, x squared plus y squared is equal to 1. We can pretend that the left-hand side is a function of x and y, and the right-hand side is just a constant. And so if we take the partial derivatives of that to get a differential, we're going to get the derivative of x squared plus y squared with respect to x is what? 2x, right? And the y is gone. So we would write 2x and the differential dx. Now the derivative of x squared plus y squared with respect to y. 2y, x squared is a constant, that's gone, so it's just 2y. And the derivative of 1, if you remember your Calc 1 implicit differentiation, a common mistake is to forget the derivative of a constant, and then you just have something weird. So anyways, this is an example of a differential. And we can look at this as a differential equation because it has derivatives in it. And if you want to force to make it look like a differential equation, you can do the dy dx business. So if we bring the negative 2x on the other side, negative 2x dx, and then divide by dx, we get dy dx is equal to negative x over y. We've seen that before, haven't we? I think when we first started to talk about slope fields, this was one of our first examples, and we actually saw that this generated slope fields of circles. Okay? You guys see connections? No. I forgot to adjust my paper. All right. So what we're going to do is we're going to define what's called an exact differential equation. So a differential equation can be of this form. We're just kind of showing that. And a differential equation that's written in this form is called an exact differential equation. If it corresponds to some differential equation of some function of two variables, f of x, y. So kind of like this example that we have, this is an exact differential equation because we can find a solution for this by looking at this f of x, y is equal to some constant. So we have an exact differential equation if the expression on the left-hand side is an exact differential equation. Oh, it's an exact differential. So we went from the f of x to the actual differential. In fact, we went from the f of x is equal to a constant to the actual differential equation. But our task is to look at a differential equation and to look at this differential portion of the differential equation and see if we can go back and find the f of x. So what we did is essentially took the derivative. We want to go integrate to go back. And so that's going to be our issue or our problem. And again, it relies on some Calc 3 stuff, but we're just going to brush over the theory behind the Calculus 3 stuff and just talk about how to get there. And so for us to take a look at a differential and know that that differential has an actual solution that we can find, we need a special way to look at it, a quick way to look and check to see if this is going to work. So we're going to ask ourselves, is this going to work for us? If we look at a differential equation, is this an exact differential equation that we can go back and find the f? The f with an x and a y. And so we need a quick way to check. So this is going to be the quick way to check. The criterion for exact differential equation is that if we have a differential expression with a dx and a dy, what we're going to do is we're going to take a look at those two functions next to the dx and the dy. So the function next to the dx we usually call m, and the function next to the dy we'll usually call n. So if we take a look at those two functions, and if we take the derivative of m with respect to y, remember m is the one next to the dx. Is that confusing? Using our simple example, I mean, our example is so simple that this is going to be like really. If we take a look at this expression, we're going to look at the function next to the dx as m, and we're going to look at the function next to the dy as n. And what we're going to do is we're going to take the derivative of m with respect to y. So opposite of the dx business, right? What's the derivative of 2x with respect to y? 0, right? And then we take the 2y, take the derivative of that with respect to x. And then if these two are equal to each other, then we have an exact differential, and therefore we have an exact differential equation. All right? So that's the part where we're checking if it's an exact differential equation. Now that we know that this is an exact differential equation, we need to find out the original function. So now that we know it's an exact differential equation, we need to find f of xy. And we're going to do that by trying to remember where the m and the n came from. So if we go look back at the beginning over here, we have an f of xy is equal to c. This is the m, and this is the n, right? So m is the partial derivative of some function with respect to x. Is that confusing yet? So if we were looking for f, which is what we want to find f. If we were looking for f, what do we need to do to this expression? Integrate with respect to? No, because it's with x. So it's the function, and we took the derivative of that function with respect to x. And so we want to undo that. It's different from this. Right? Yeah, so this part over here is just to find out, it's related to this. I should do that in blue. This part over here is to find out if something is exact. Once you know that it's exact, then you want to try to go back and recover the original function f. And to recover the original function f, we have to look back and say, wait, this function m was actually the partial of f with respect to x. To check it, yes. Yes, yes. Yes. So the first part, this part over here, is finding out if this is exact And we can say yes in this case, it's exact, and then we go on. If we do this and we find out that these two things are not equal to each other, then we stop and say it's not exact, I can't solve for this. And then there are other tricks to try to solve for this by finding some integrating factor or something like that, but in some cases we just leave it alone. And that's the thing with integrals, right? You guys have gotten into some integrals and say, oh, I can't integrate this. This is not integrable. So that happens here because we're doing the integration part. So after you did find out that this was exact, then you want to try to recover the original function. So what's the original function? The original function is f. You're looking for f. So if you're looking for f, you want to integrate your expression with respect to x. So if I integrate m with respect to x, that's like integrating this partial with respect to x. And in our example, it was 2x. All right. So the stuff in red on this page, it's all referring back to this problem here over here. And so when we're doing our work down here, hopefully we get the same answer as what's up there. What's the antiderivative of 2x? X squared plus c. Now here's another tricky part in this whole scenario, is that we're dealing with two variables, x and y. We're integrating with respect to x, and we have a plus c that's constant. Y is a variable, but it's constant with respect to c, right? So it's possible that there's a y in this expression that would have disappeared if we would have taken the derivative of it. So instead of just a regular c for constant, so instead of a regular c for a constant, we'll call it a constant and maybe some function with a y in it. You could do that. I don't like doing it that way. Yeah, I know. A lot of people do that. I don't like doing it that way. So there's some lights dinging on some people who have taken Calc 3 before, which is good, I guess. And if you haven't, don't worry. This is a better way of doing it. Yeah, you could tell them I said that. Oh, I'm being recorded here. Stop talking shit. So similarly, with the function that's being multiplied with a dy, you want to undo that with respect to y. And then again, in our example, our dy is n, which is 2y. And again, y is the variable we're integrating with respect to. That means a constant was any constant or maybe an x. So this could be a function of x. What? And so the thing to do here is to combine these two results. Now, some people from Calc 3 up here in the front were saying, oh, you take the derivative of this with respect to y and then blah, 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 and then compare it. So what I do is I like to just go through it from the two separate functions, and then I get these results, and now I compare this. So that might be a little bit, I don't know, I think it's a little bit more intuitive, but it's less systematic. Well, what I'm going to do is I'm going to gather all the functions that are different. So if it's the same, then it might happen on the same thing. And so I'm not going to put those two functions together. I'm just going to look at the different functions that are involved here. And then I'm going to assume that everything else that happens after that would be constant. Or I can just say that this is my f of x function, f of xy. And so my answer is going to be this thing is equal to c. And that's it. And if you had an initial value, then you would put your initial value in, and then you'll be able to solve for c. Okay. All right. So that's kind of like the rundown of this thing. Let me do one more problem, and then maybe you guys can give this a try. I don't know if this is enough room to do a problem. Whole mess of problems here. Yeah, let's do number one. No, let's do at least let's do number two, because there's a mix of x and y's in each of these things. So nobody's gonna jump on the sine and cosine one. Not anymore. Not after the first time. All right. So I don't know if this is even exact. So the first thing we have to do is check if it's exact. Say it again. Yeah. And if there's a negative, make sure you include that, because that'll be important for us. So now I want to take the derivative of this thing. So let's see. First, we're checking if it's exact. So we need to take the derivative of m with respect to y, which is what? 1. This is what? It's negative 1. Oh. So I think we're done with this one. Well, there might be ways to try to continue to solve for this, but let's just be done for now. Okay, so if it's not exact, then you can't go through the process that we just did. Let me see. I need to find another example. We can find one that's exact here. Now let's try number 5. All right, let's do another check. Got m. This is m with respect to y, 4x, y, and the 3 is gone. And then the n with respect to x, 4x, y. So this one is exact. So now we continue. We have to try to find the function where this originally came from. So now we need to take a look at m, not m sub y, but m itself. And we want to integrate m with respect to x, because it was the original function. We took the derivative of the original function with respect to x to get m. And so we want to go backwards. So it's 2xy squared minus 3 dx. So with respect to x, y is constant. What's the derivative of 2x y squared? X squared. It's 2x squared over 2, right? So the 2's would cancel, and the y squared. And then we have a 3x. And then a constant, and remember we took the integral with respect to x, so there's a possibility that there's a y in there. So we'll call it g sub y. And then we'll take the integral with respect to integral of n with respect to y. And I think we're going to get something similar. We're going to get x squared, y squared from this one, 4y from this one, and then f of x, or not f, h. All right, integrals look okay. So now what we want to do is we want to compare these two things so we can try to see what the original f function is. The original f, a function of two variables, x and y. So between these two, I see that x squared, y squared is in common, right? Now I'm only going to write that one time because they're both here, and that means that must be the thing that they share, that they have in common. So that must mean that f of x y is equal to x squared plus y squared. And now I have a g of y here that probably would correspond to this 4y that I found in the second function that made it disappear in the first function. Yeah. Yeah. Magic. And then likewise, there's a negative 3x that happened when I took the derivative with respect to x, but when I took the antiderivative with respect to y, it didn't pop up because it would have disappeared in a derivative. So I would count these two as my other functions, and then I would have a plus c or minus c, plus c. What? Word. So remember that this is not the answer. I've marked people off wrong for having this as an answer. The answer is an implicit function of x and y without the f of x business. And so what I'm looking for as an answer for a problem like this would be essentially this x squared y squared plus 4y minus 3x is equal to c. I just moved the c over to the other side and threw away minus. Luis? Let's check if it's correct. So the way to check if this is correct is to take the differential, take the derivative with respect to x and y, and see if we obtain the original function. So let's check that. C. Oh, yeah. The thing about C is that we can call this a different C. When we bring it over to the other side, it's still a constant, right? But we don't know that constant from the beginning. So when we bring it over to the other side, then we can just call it a different C. That doesn't matter. So the thing about constants, and this is kind of weird, when you have constants and then you do something like put a negative sign or multiply it by just a number or divide it by just a number, when you do things with a constant and you're doing just number things to it, then you could just call it another constant. If you have a constant and then you're multiplying it by x, that's different. Okay. So remember when we did e to the x plus c, and then we said e to the x times e to the c, and then we'll say e to the c is just a constant, and then we just called it another constant, a e to the x. That's the same thing as throwing that negative sign in front. It's still a constant. And I know it's confusing, and it's really dangerous when you're plugging in for an initial condition. If you plug it in somewhere along your work, then you have to replace that constant that might have changed along the way. So, all right, so this is f of xy. And then what we want to do is we want to take the differential of this. So take the derivative first with respect to x and then multiply times dx, and then take the derivative of this with respect to y and multiply times dy. So this is what we want to do here. We want to multiply with take the derivative with respect to x and then multiply it with dx plus the derivative with respect to y and then times dy is equal to, and then the derivative of constant is 0. So that's what we want to do. Let's do that. The derivative of this thing with respect to x, y is a constant, so this is 2x, and then y squared is constant, so it doesn't move. So 2x, y squared. 4y goes away, and then minus 3, and then that's it, right? So that's the derivative of your function with respect to x. And now you want to take the derivative of your function with respect to y. So with respect to y, we're going to get something similar, and then 4, and then the minus 3x went away with respect to y. So we're done. Put a dy, and then the derivative of a constant is 0. Exactly what we started off with. Yeah. Right. So it looks like you're adding them, but you're not. What you're doing is you're trying to figure out the original function that was given to us, or that essentially what you're trying to find is that function, the original function, where these two derivatives came from. You're assuming that these two functions are derivatives from the original function. So when you're taking the antiderivative and then you see two functions that match each other, then that comes from the same function f. So this is what we're looking for, f. And so that when you took the integral and you found x squared y squared plus something, x squared times y squared plus something, and x squared plus y times y squared plus something, then the x squared plus y squared must be the same function that they have in common. That's common to both of them. Now imagine if you would have added these two things, then you would have had a 2 over here. Let's do this in a different color, and then I'm going to undo it. Imagine that you had a 2 there, and then when you came here to check, then you're going to get an extra 2 over here, which then would be different from your original differential equation, which means there was something wrong. Okay, so undo. I get everything? Yeah. So when you see something in common, when you're at the step and you see something in common, just put it down one time. And all the others that are not in common, you're going to have to assume that there's a 3x here and there's no y, so that must match up with the h of x. And then there's a 4y here, that must match up with a g. That's why this method is a little bit trickier from how you might have learned it in Calc 3. But if you just remember that if it's the same, you count it once, and if it's different, then you count it. Okay? Any questions? All right, let's do one more with an initial condition. There must be some with initial conditions here. All the way down there. All right, 37. So with an initial condition, all we have to do is worry about solving for C. Instead of there's a plus C or there's a equal C on the other side, we're just going to solve for that. All right, let's see. We should always check if it's exact before we go. So this is your M. You want M with respect to, oh, this isn't even exact. Sorry. Here's some that are number 21. Oh, look at 22. What? All right. E to the x plus y times dx plus, and then we have a 2 plus x plus y e to the y times dy is equal to 0, and then we have an initial condition y of 0 is equal to 1. So let's see, let's first check if it's exact. I hope it is. Your m function, you want your m with respect to y, that's just 1. And then your n function, you want your n with respect to x, and that's also 1. Okay, exact. So now that it's exact, we have to see, let's see if we can find out our actual, whoops. Oh, I just closed it. All right, here it goes. Once we find out that it's exact, we can go on and find the f function. So we'll take your f function is hopefully going to equal to the integral of m with respect to x. So the integral of e to the x plus y dx, and that's equal to integral e to the x, integral of y It's xy, right? With respect to x. So it's not y squared over 2. It's pretending y is a constant and you integrate with respect to x. And then allow for some other terms that might just have a y in it. Now this is hopefully equal to our n function with respect to integral of n with respect to y. So that's 2 plus x plus y e to the y dy. Oh, are you kidding me? Yeah, so it's 2y plus xy plus y e to the y minus e to the y. Integration by parts? Is that right? All right, good. All right. So now, again, the tricky part is to look at this and compare. I'm first going to gather the terms that are the same, and I know that the same terms are going to be accounted for one time. So f of x, y is equal to xy plus. And now I'll take a look at the other terms that are not equal to each other, but they probably would be living in a g of y and an h of x functions. So I have an e to the x here. I have a 2y here. And then I have this other business here, y e to the y minus e to the y. Now remember that this is not my final answer, or you have to say equal to c. So it's actually equal to 0, and then the c goes off on the other side. But without the f of xy, just the function itself, so that's xy e to the x plus 2y plus y e to the y minus e to the y is equal to 0. Whoops. Is equal to a constant. This is not the final answer for this problem, but if you didn't have initial conditions, you'd be done, because this is a general solution. Okay? So now, to find the particular solution, you would want to put 0 in for x and 1 in for y. Okay? And if you do that, you'll have the c already on the other side. So 0 in for x, 1 in for y. What is this? 3? Okay. So then your final answer, particular solution, you would leave it, you would say equal to 3 on the other side. So xy plus e to the x plus 2y plus y e to the y minus y is equal to 3. Oops, the last one. Yeah, and then there's a 2 here. So those are the only two things that contribute, because this would cancel and then you have 0. Is that right? So this is where you want to be careful about with the plus c. Yasmin asked about the minus c or the plus c on the right hand side, and we brought it over, it became a negative. So if we just kind of forget, let's just forget about this business over here, and always remember the plus c is on the right hand side of the equal sign, so that if you do have initial conditions, you just plug it in and you get the c solved for already. Then I think that'd be easier to remember. Luis? Some people don't put equals C or equals whatever the right hand side is. So actually, this is what they put for their answer. Because it's not an equation that has an equal c on the other side. It has to have an equal c on the other side. So this is the most common wrong answer that I get. And it's not really that wrong. It's just that you're not writing your final answer correctly. So make sure you write it with an equal c on the other side. Yeah, so the general solution, if there's no initial conditions, then there's a equal c, and that's what's needed. Even a particular solution, this won't work because there's a, yeah. All right. Any questions? All right. Why don't you guys take a minute or two to start one of these problems? Let's pick one with a, let's, well, I'm trying to think if 9 is exact, because these problems 1 through 20 may or may not be exact. I don't know if I could do it in my head. I can't do it in my head. Yeah, so 23, they just change a variable on you. Why don't you try that? So let's do number 23. You guys do number 23. I'll give you like a couple minutes to start, and then I'll try it myself. Yeah, work on it. Oh yeah, if you want to talk to other people, go ahead. All right, see how far you can get with this. All right, let's take a look at what we have so far. I think this is, I hope this is correct. Um, and then now we just let it equal to C, and then use the initial condition when t is equal to -1, y is equal to 2. So we got 4, -1, 2, plus -1 squared minus 5 times -1. Oh, 3y, y is 2 squared minus 2. What is this? 8, -8 plus 1 plus 5 plus 12 minus 2. 8. 8. And so remember to write your answer, the answer that you would eventually box, maybe I shouldn't have boxed 8, but the correct answer would be your final answer, 4ty plus t squared minus 5t plus 3y squared minus y is equal to 8. Okay. All right. So now let's address the possibility, the likelihood that we don't have an exact differential equation. If we don't have an exact differential equation, but it looks so close that we would really like it to actually be exact. Just like we did last section, we can come up with an integrating factor. Although these are really special cases. And they have a couple of criteria here for the integrating factor. So if you can calculate these expressions over here, my minus nx divided by n, if that thing turns out to be a function of just one variable x, then you can multiply it by the integrating factor. This is e, the exp is e raised to the integral of that big thing. It only would work for these special cases. Well, there's one that wasn't exact, right? Although I probably don't want to do that one. Well, I pick a problem that says this is not exact, multiplied by an integrating factor to make it exact so I know that it'll actually work. In Calc 2, I used to just make up integrals and do them, and I would often get stuck because you can't do all integrals, and you can't take integrals of all the functions. So I think I've learned over the years not to try things. So like here, problem 29 and 30, verify that the given differential equation is not exact, and then multiply the given differential equation by the indicated integrating factor, or here they actually give you the integrating factor so that it becomes exact. I'd rather do that one. Or maybe even 31 through 36, come up with an integrating factor. All right, let's challenge ourselves. Sure. Let's do 34. Oh, I don't know if this parentheses, does anybody have the book open? Is this parentheses around 1 plus 2 over y, or does it include the sine x? You have the book open, don't you? You think? I don't know. I'm scared now. All right, let's do number 33. It does or does not? It doesn't. It's too late. I don't want to mess with sines and cosines. All right. So we can verify that this is not exact. We can see if this is your m, this is your n, mx or my is 6x, and nx is 18x. So these two are not equal. Now it says if I do the my minus nx divided by n, if I get a function of x alone, I can multiply it by this. Or if I switch the order, divide by m, and it's a function of y. So let's see what happens. Let's try the first one. My minus nx divided by n. That is my. It's 6x minus 18x divided by n. N looks complicated. 4y plus 9x squared. So this simplifies a little bit, but it's a function of, I see a y here in the bottom and an x. So this is not a function of, not f x. So there's two variables involved there, so I can't use that first criteria. So let's try the other way. Nx minus my divided by m. And so that's 18x minus 6x divided by 6xy. That's positive 12x over 6xy, and that cancels 2 over y. So this is a function of y alone. So if I multiply by the integral of that with respect to y, or the exponential of the integral of that with respect to y, then I have a chance of making this exact. All right, so what are they asking here? They're asking us to say this is what we want to use. We're going to say mu of y is going to be e raised to that. Now this expression is the same thing as the thing that we just found, right? So we just found that to be 2y. So this is really 2y, 2 over y, dy. We have to integrate, and so we have to call it the 2y, or 2 over y. Is it? So e to the 2 ln of y. Is this, what is this? What does this simplify to? This simplifies. It looks like it simplifies. What? Y e squared? What do you think it is? No, you can't separate it because you're not adding. Y squared. And oh, there you go. Right? The 2 becomes a power of y, e to the ln of something is. Everybody goes, oh, right. All right, so let's multiply the expression by this y squared. So this is our integrating factor, and we're going to multiply this by y squared. And so if we multiply this by y squared, we're going to get 6xy cubed in the dx, and then 4y cubed plus 9x squared y squared dy. Now this is hopefully exact. Let's check if it's exact. Yes. Yeah. And so I'm assuming this is exact already, and I could just do the procedure. But I want to check to make sure if it's exact, to make sure that we did it correctly. No, if you tried to make it exact and it didn't work the first time, then yeah, or you did something wrong. We did something wrong in the calculation here, which is also quite possible. But I'm hoping this is exact. Let's check. This is your new m and your new n, and so my is equal to, this is 18xy squared, nx is equal to, this is going to be 0 and 18xy squared, and they are equal this time. So now we have exact. And then now you go ahead and work it out. And by you, I mean you, because I'm done. All right? I'm out of, oh, I thought I was out of room. All right, I'll do it. like my kids, finding excuses not to do stuff. All right, M. So our function that we're trying to look for, we'll integrate M with respect to X. And you can skip some of these like little things that I'm writing here. Maybe skip this integral M dx because it's always going to be the case. 6xy cubed dx. So with respect to x, that would be x squared over 2. That would cancel with a 6. 3x squared y cubed. Plus some constants that may have y's in it. And then I would integrate the second new n with respect to y. That's the integral of 4y cubed plus 9x squared y squared dy. And that is going to be, this is a 4. Y to the 4th over 4. That's y to the 4th plus. And then 3x squared y cubed plus h of x. And so I see something in common here. I'll write that only one time. And then all the other terms that are around, I'll just write. And so my final answer should be 3x squared y cubed plus y to the 4th is equal to some constant. And there's no initial conditions. So we're done. Okay. All right. So you guys have homework or something? All right. Good luck with that.